T-test. The concept of statistical significance for comparing means is based on the relationship between two sample characteristics, the mean and the variance. The difference between group means indicates the degree of separation between groups, the effect size. Variance measures tell us how variable the scores are within each group. Both of these characteristics represent sources of variability that are used to describe the extent of treatment effects. Suppose we wanted to compare two randomly assigned groups, one experimental and one control, to determine if treatment made a difference in their performance. Theoretically, if the experimental treatment was effective and all other factors were equal and constant, all subjects within the treatment group would achieve the same score, and all subjects within the control group would also achieve the same score, but scores would be different between groups. As illustrated in figure 19.1a, everyone in the treatment group performed better than everyone in the control group. Consider scores in this sample for both groups combined. If we were asked to explain why these scores were different, we would say that all differences were due to the effect of treatment. There are differences between the groups, but no variance within the groups. Now, let's consider the more realistic situations where subjects within a group do not all respond the same way. As shown in figure 19.1b, the scores in the treatment and control groups are variable, but we still tend to see higher scores among those who receive treatment. If we look at the entire set of scores and we are asked again to explain why the scores are different, we would say that some of the differences can be explained by the treatment effect. That is, most of the higher scores were in the treatment group. However, the scores are also influenced by personal characteristics, inconsistencies in measurement, and behavioral and environmental factors. These factors create variance within the groups, variance that is unexplained due to all other unknown factors influencing the response. This unexplained portion is called error variance. The concept of statistical error does not mean mistakes or miscalculation. It refers to all sources of variability within a set of data that cannot be explained by the independent variable. Any given score is a composite of the treatment effect and the error variance. Random assignment allows us to assume that these error components are unsystematic chance variations and therefore are independent of the treatment effect. The distribution in figure 19.1b is represented by a pair of curves. This graphic shows means that are far apart with few overlapping scores, the gray area at one extreme of each curve. The curves show that the individuals in the treatment and control groups behaved very differently, whereas subjects within each group performed within a narrow range. Error variance is small. In such a comparison, the null hypothesis would probably be rejected as the treatment effect has clearly differentiated the groups. Contrast this with the distributions in figure 19.1c, which show the same means but greater variability within the groups as evidenced by the wider spread of the curves. Factors other than the treatment variable are causing subjects to respond very differently from each other. Here we find a great deal of overlap, indication that many subjects from both groups had the same score, regardless of whether or not they received the experimental treatment. These curves reflect a greater degree of error variance. That is, the treatment does not help to explain most of the differences among scores. In this case, it is less likely that the treatment is differentiating the groups, and the null hypothesis would probably not be rejected. Any group differences observed here are probably due to chance variation. To make an objective decision about whether or not to reject the null hypothesis, we make the decision on the basis of its probability of being true. This is what a test of statistical significance is designed to do. The significance of the difference between group means is judged by a ratio illustrated in the equation at the top of the page. The numerator represents the separation between the groups, which is a function of all the sources of variance, including treatment effects and error. The denominator reflects the variability within groups as a result of error alone. Therefore, when null hypothesis is false, that is, when a treatment effect does exist, the ratio is conceptually represented as the equation pictured in the center of the page. When null hypothesis is true, that is, when no real treatment effect exists, the ratio reduces to the equation pictured at the bottom of the page. As the treatment effect increases, the absolute value of this ratio gets larger. As the error variance increases, the ratio gets smaller, approaching 1.0. If we want to demonstrate that two groups are significantly different, this ratio should be as large as possible. Thus, we would want the separation between the group means to be large and the variability within groups to be small. We emphasize the variance between and within groups as essential elements of significance testing, which will be used repeatedly as we continue our discussion. Most statistical tests are based on this relationship. This schematic depicts a research notation of a study with two treatment groups and one control group. Each treatment group is represented by a capital R. The top R is a group that receives neuromuscular electrical stimulation, and the bottom R is a group that receives progressive quad strengthening. The control group is at the bottom and receives no treatment. Outcome measures are represented by a capital O and are taken for the two treatment groups at baseline, 3 months and 12 months follow-up. Outcome measures for the control group are only taken at 12 months follow-up. There are 41 subjects in the control group as represented by the number in the schematic. The schematic also represents between and within group comparisons. The horizontal green arrows represent within group differences, while the vertical green arrows represent between group differences. Comparisons are made between the two treatment groups and between the control and treatment groups. Recall that before statistics are generated, we need to determine if there is equal variance among groups. This is done with a homogeneity of variance test. This test will clarify if the observed difference in variances is large enough to be meaningful. When variances are significantly different, they are not equal. Adjustments can be made in the test of means that will account for these differences. In some cases, non-parametric tests will be used. If you go back to figure 19.1d, you can see that the variance between the groups is not equal. The variance in the treatment group is much less than the control group. In this situation, the two groups have different variances, and the assumption of homogeneity of variance is not met. Now, let's talk about the t-test. The t-test is a statistical procedure used to compare two means. The independent or unpaired t-test is used when the means of two different independent groups of subjects are compared. Now look at figure 19.2. There are 20 subjects, each randomly assigned to either the experimental or control group. Pinch strength is tested on day 1. The experimental group receives a hand splint while the control group performs regular activities. Pinch strength is reassessed on day 8. We are looking at the difference between the change scores within and between the two groups. This is an example of a typical statistical output that you will see with a t-test for independent samples. Don't panic, you are not responsible for the math, but you might be remotely interested in knowing where the numbers come from and what they mean. Under the group statistics, you can see the two groups' means and standard deviations. Under the independent samples test, the Levene's test for equality is the test of homogeneity. Looking at the black circle with a 1 inside it, you see that the difference between the two groups is not significant. Therefore, we will use the t-test for equal variances. Looking at the black circle with a 2 inside it, we see that the two-tailed outcome is 0.014. The analysis is actually based on a one-tailed test because we have a directional test with an alternative hypothesis. Researchers expect the treatment group to have a larger change in mean compared to the control group. You can see this if you look at hypothesis testing C, figure 19.1 in your textbook. You will see that there is both a null hypothesis and alternative hypothesis. Therefore, this 0.014 is divided by 2, and now probability equals 0.007 and is considered significant. We will review this again in class, but try your best to follow along. Critical value of t is used to determine if the calculated t-ratio is sufficiently large to be considered significant. We do this by comparing the calculated t-value with a critical value at a specified level of significance. The larger the ratio, the more likely the difference is not due to chance. Table A2 in Appendix A is a table of critical values associated with t-distributions for samples of various sizes. Without getting into the math equation too much, the critical values of t is a product of alpha and the degrees of freedom, number of subject minus the number of groups. In the example, alpha equals 0.05 and degrees of freedom equaling 18, the critical value is 1.734. We find this in Table A2. The null hypothesis states that the difference between means will be 0 and therefore the t-ratio will also equal 0. The probability that the calculated t-ratio will be as large or larger than 1.734 is less than 5%. For a t-ratio to represent a significant difference, the absolute value of the calculated ratio must be greater than or equal to the critical value. In this example, the calculated value t equals 2718 is greater than the critical value of 1.734. Therefore, the group means are considered significantly different at alpha equaling 0.05. We reject null hypothesis and accept alternative hypothesis and conclude that patients wearing the hand splint improved more than those in the control group. When sample sizes are unequal, differences in variance can affect the accuracy of the t-ratio. If the test for equality of variance show that variances are significantly different, the t-ratio must be adjusted. Consider the previous example, in which we examine the effect of a hand splint on pinch strength. Table 19.2 shows alternative data for this comparison with unequal sample sizes. The variances in this analysis are significantly different. Levine's test, probability equals 0.038. Look at the black circle with a 1 inside it. In this instance, we will use the second line of data in the output, equal variances not assumed. The findings for this analysis are significant for a one-tailed test. We reject null hypothesis. We will review these slides in class. Now, let's consider another statistical procedure. In this scenario, we set up a study to test the effect of using a lumbar support pillow on angular position of the pelvis in relaxed sitting. We hypothesize that pelvic tilt will change with use of a support pillow, a non-directional hypothesis. We test 8 subjects, each one sitting relaxed in a straight back chair with and without the pillow, in random order. Because each subject is measured under both experimental conditions, this is a repeated measures design, testing the hypothesis where means represent repeated conditions. Here is a statistical output for the analysis. There is an error. The black circle with a 3 inside should be in column 3, not column 2 of the paired samples test. Again, we will review this in class. Although we will review in class, please make every effort to try to understand the outputs in terms of significant result versus not a significant result. T-test is the most commonly applied statistical test. Unfortunately, it is also one of the most misused. The sole purpose of the t-test is to compare two means. Therefore, when more than 2 means are analyzed within a single sample, the t-test is inappropriate. For instance, if we wanted to compare 3 types of exercise, it would be incorrect to use the t-test because the analysis involves 3 comparisons within one sample. The problem with using multiple t-tests within one set of data is that the more comparison one makes, the more likely one is to commit a type 1 error. That is, to find a significant difference when none exists. Remember that alpha is the probability of committing a type 1 error for any single comparison. At alpha equals 0.05, there is a 5% chance we will be in error if we say that group means are different. Although it is true that alpha equals 0.05 for each individual comparison, the potential cumulative error in a set of comparisons is actually greater than 0.05. Consider the interpretation that for alpha equals 0.05, if we were to repeat a study 100 times when no difference really existed, we could expect to find a significant difference 5 times as a random event just by chance. 5% of our conclusions would be in error. For any one comparison, however, we cannot know if a significant finding represents one of the potentially correct or incorrect decisions. Theoretically, Any one test could be in error. Consider a different random event, such as a strike of lightning. Suppose you had to cross a wide open field during a lightning storm. There may be only a small risk of getting struck, perhaps 5%, but would you prefer to cross the field just once or several times? This same logic applies to repeated t-tests. The more we repeat comparisons within a sample, the greater are our chances that one or more of those comparisons will result in a random event, a significant difference even when one does not exist. This problem can be avoided by using the more appropriate analysis of variance, ANOVA, which is a logical extension of the t-test specifically designed to compare more than two means. As an adjunct to ANOVA, multiple comparison procedures have been developed that control the type 1 error rate, allowing valid interpretations of several comparisons at the desired alpha level.